All right, so in number 21, we're given this position function. And so what that means is that if we input any value t, where t is in minutes, this is going to output the position that this particle is along the x-axis. And the question says, what is the average velocity from t equals 0 to t equals 2? And so if you think about, well, what is velocity? Well, velocity is your change in position over your change in time. So let's write that down. That's my average velocity. Average velo, change in position over change in time. Well, we just need to plug some stuff in. So I need to know, what is my change in position? Well, to do that, my change in position should just be my position at the end minus my initial position. And then my change in time is, of course, my ending time and my starting time. If I plug in 2, if my math is correct here, I get 3. So my position when time equals 2 is 3. My initial position when time equals 0, if I plug 0 into that function, is 15. And then over 2 minus 0, simplify that, and we get negative 6. Sometimes people say, well, that's strange. How can we be going negative 6 meters per minute? Well, negative velocity just means you're going backwards. And we can see that. We started at 15 on the x-axis, but we ended at 3. So we went backwards a total of 12 units, and it took us 2 seconds to do that. So on average, we went backwards 6 meters every single minute. And so that's what we mean here by average velocity. Also, super important to notice, this time we used average velocity, but this is just slope. Velocity is just one special rate of change, and so any average rate of change is just slope. 22 is asking us to remember some of our properties of logarithms. So as I look at this, I'm looking and I'm thinking, okay, there's a lot of choices here. So I'm just going to start kind of simplifying this and say, okay, well, what would I usually do? And usually with logarithms like this, the first thing I'm going to do is I'm going to split up the numerator and the denominator. And we know that we can break one logarithm with a fraction into 2 separate logarithms separated by subtraction. So I'm going to have log base 4 of x squared minus 6x plus 9 minus log base 4 of 16. And how nice that's option 1. Okay. Be careful here. Sometimes a mistake that people make is they forget this second logarithm. And what that means is that, you said if you forget this second logarithm, you're saying that division and subtraction inside logarithms are the same, which they are certainly not. You can either divide inside the logarithm or subtract after taking the logarithm, but we need both these logs here. And then I can start thinking about how could I simplify one or both of these pieces a little bit further. And notice that this one is 2. Log base 4 of 16 is 2, because remember what a logarithm is saying is what is the exponent that I would put on this base so that this would be my answer. 4 to what power equals 16? Well, 4 to the second power is equal to 16. And hey, how nice. That's actually my second choice here. And I think yours will be scrambled in a different order than what I have here. It just happened that mine were the first 2 choices here. Now, can I simplify this first chunk any further? Yes, I can. I can factor this and then break that multiplication down into addition. So this would be log base 4 of x minus 3 plus log base 4 of x minus 3. And all I've done again is I've just taken this what's inside and I've factored it, and then I know that just like division inside a logarithm can be broken down into subtraction outside the logarithm, multiplication inside the logarithm can be broken down to addition outside the logarithm. And these two are actually the same, so I could combine that and make it 2 times log base 4 of x minus 3. Let's see what we have here to consider. So this looks almost like what I have, except for this is a plus, this is a minus, so no to this one. This one is interesting. This would actually work because, like I said, we could have 2 of these, and then we've just factored out a 2 to get that expression. In this next example, or choice, I should say, it looks a little bit crazy with all these fractions here, but because we had a monomial in the denominator originally, you can just divide each individual term by 16. And so this is x squared over 16 minus 6x over 16 plus 9 over 16. And that's totally fine. You can divide each of those things up individually like that. But what you can't do is just then all of a sudden turn those into separate logarithms. That doesn't make any sense. So no, not okay. But if we jump down to, sorry, keep my color scheme here. No. If we jump down to this one here, well now I did that same simplifying, but it's inside the logarithm. So that actually works. Kind of skipped over this one here in the middle. This one we skipped looks almost exactly like the first one. We just mixed up our pluses and minuses, so be careful there. Same deal on this next one. It looks like exactly like the second one, which was good. So good, bad. Now this next one, that actually looks like what we have here, except that we didn't simplify this last bit. We left that as minus log base 4 of 16, but we did the same thing up here. So that actually looks good to go. And then this last choice, well, it's this whole factoring out the 2 situation, but we've got the wrong sign again there. So good try, but no. So that was a lot of fun. Let's do another similar one, practicing our properties of logarithms, but now kind of going the other way. We're taking these 2 logs and we're trying to put it back together somehow using those properties of logarithms. So again, I'm just going to think about, okay, well, how would I do this? And then that'll help me get started. That'll help my train of thought. Sometimes if you look at a problem like this and you're like, oh my goodness, like, how am I supposed to figure out all 6 of these choices here? It's just so much. So I just say, well, let me think about it by myself for a second. And so what I would do originally here is I would combine this. I've got 2 separate logarithms being subtracted. So I know I can make that one logarithm, 36, where they're being divided. Just the opposite of our first step in that previous problem. And hey, isn't that nice? That's my last choice. Wonderful. So that's good. Now, in the last problem, we were able to factor and break things up further that way. So let's try that as well here. And look, the numerator does factor, so that's nice. This is x minus 6 times x plus 6 over x plus 6. the x plus 6's can be canceled out, leaving us with just log base 3 of x minus 6, which is that choice. This one here, we'll continue with our black x out. This is trying to do what we did in the first step, taking the subtraction and turning it into division, but they did it as two separate logarithms, which is no, because again, that's what you're saying there is that as long as you're taking a log, subtracting and dividing are the same, but that's not what the property says. The property says if you have two separate logarithms with the same base being subtracted, you can combine that into one logarithm where you first divide what's inside the logarithms and then you take the log. Here we kind of canceled out the x minus 6 sort of, but all the logs got canceled out as well, so I don't think so. Looks like in this one we tried to pull a 2 out by taking this 2 and maybe that 2 out front, because we know that if you have an exponent inside the logarithm, you can in fact pull that exponent out, but that would only work if the entire thing was squared, not if each individual term is squared, so that's no good. And I think here what we've tried to do with this first one is we tried to turn this minus into division and this plus into multiplying, but that doesn't work. It's kind of backwards of what the property says. So no and no. All right. I think last question for this video. We're given this composition of functions, natural log of 2x minus 1. And we're told, okay, that's h of x, and h of x can be thought of as f of g of x. Well, what could we do? What could we call g of x, and what could we call f of x? It's what's the inside function, what's the outside function. And for me, the easiest way to see that is that that inside part, g of x, is 2x minus 1, and the outside part is the natural log of x. Because if you followed the process and did f of g of x, you would take this g of x and put it in for x in f of x, and that would give you ln of 2x minus 1. You could also do this as the g of x as just 2x, and the f of x as ln of x minus 1. And then this 2x goes in for just this x, and we'd have the same result. Either one is fine. Both will be accepted by Schoology.